Welcome back, everybody. This is part two of an exciting series. That is part two of this exciting series on nonlinear regression. Let's dig right in and pick up where we left off. Here we go. Okay, so we finished looking at some residuals. We rejected the linear model and based on the patterning in the residuals and our own intuition, just by looking at the way the points are scattered about the graph, that something nonlinear is more appropriate. So I'm just going to move the residual plot off to the side for now. And I'm going to keep the linear model there for comparison purposes. So in fact, what I'm going to do is, to save myself some time, I'm just going to copy the whole graph. Oh, that's not what I wanted to do. Let's see if I can copy that graph, save myself some time and ourselves some time when we're working with this. Let's see if it actually overlaid. It did not. Try that one more time. There we go. Perfect. Okay. So copying the graph very quickly, or you could just insert a new chart and go from there. Just deleting the equation. With the trend line, I'm going to format the trend line. And what we're going to do is we're going to select, in this case, there are two selections we can make. I'm going to select exponential. Okay, so we're going to use exponential. We won't be using logarithmic or power or moving average. We will be using a polynomial and an exponential function. So exponential function, which is used to model exponential growth and decay, depending on the situation that you're studying. Okay, so bacterial growth, population growth, compound interest, those are all examples that require exponential growth. And then exponential decay, for instance, would be half-life. Okay, so radioactive decay. So you can think in terms of the role of medical imaging and the radioisotopes that are used. You can also think of something that's meaningful to everybody is when you have ownership over a vehicle. The depreciation, that is exponential decay when you lose money or value year by year on your vehicle. So we have an exponential model here. And you can see the particular style of the equation. We have 5.6958. That is a y-intercept. And then E, that is a particular base. So it has a value. It's approximately 2.71. So that's a specialized number in mathematics. Much like pi holds a very special place in the mathematician's heart, so does the number E, which is approximately 2.71. And then to this particular exponent. Notice that the variable x is in the exponent, okay, so hence the reason it's called an exponential equation, because the variable or the independent variable is in the exponent. This value here is a scaling factor, so we won't get too far into that, but rather we simply want to be able to use functions. So notice with this one here, we've got a very beautiful looking fit. You can see that there are 1, 2, 3. Looks like we have 3 and possibly another residual value here. So we could go back and replot the residuals and it would look very different indeed based on that particular model. Now, to do that properly, you and I would have to take that equation that we have here and we would have to replace that here. So when calculating the predicted values, we would actually have to go and instead of using the linear model, replace that with the following equation. Okay, so if you have questions on how to utilize or do that, by all means, please bring that to my attention and we can quickly go over that in class or outside of class. Have a look at the R-squared value. That's excellent news. We've got nearly 100% of all of the variation being explained by that curve of best fit, so 99.5% of the variation. And if we plot the residuals, we won't see much of anything in terms of abnormalities. Those residuals should be small and very close about the line of 0, or that is y equals 0. What else can we say? Again, there are no outliers or influential points, so we've got a very good fit. One of the things we should do before accepting that model, if that's the way it's going to go, is, I'm just going to get rid of those residuals for now, And I already have this scripted in another part. So let me take you over here. You can see the same model there that we just did. Below, in fact, although I thought I had it in here, let me see if it's further here. There it is. Perfect. So here's another model. Let me show you what this one is. In fact, you've seen this stuff before. Have a look at the degree or the exponent, the highest value of the exponent on x to 2. Okay, so this is a quadratic function. The graph is a parabola, as opposed to over here we have an exponential curve. So the polynomial function has order 2, which means it's a quadratic. 3 would be cubic. Now that cubic function, check this out. Wow, 0.9974. Okay, this would be a quartic. And even better is the fit. But what we have to assess is also the reasonableness of the model to the context. So you can imagine that this shape of function wouldn't necessarily fit the trend or the pattern in how populations grow. Same thing with the cubic function. Its particular shape, it has an S-like shape. Okay, so as we approach 1 and further we go less than 1, you're going to see the shape go into more of an S-like formation. And then with the quadratic, you can get a sense of that too, where the function actually starts to go back on itself, and you can see how with a mirror image of that, these points would be reflected through a line of symmetry, probably through approximately 2 or just less than 2. So the function actually is going to be increasing in this direction here. So we will, even though we have a 0.996 value, we will be rejecting the quadratic model, okay, on the basis of its appropriateness, purely in the context, right? So contextually, we would not use this model to read population growth between 0 and 1 hour, as for the very good reason that the population, according to the model, would be predicted to be higher than it is even at 1 and 2 hours. So we do have to apply some degree of common sense to making those choices. Okay, so my hope for you is you've had a chance to see how Excel is used to not only plot data and add trend lines and curves of best fit, but you've also, as a goal, have been able to figure out all of the criteria and understand those criteria for determining if a line or a curve best fits that data. So in summary, things you should be looking for, okay, are 1, your outliers, okay? Innately have a look at them, decide big or large, look for influential points. So values extreme in X, those will have an impact on the slope and the position of your line of best fit. Okay, it will definitely skew the slope greatly. Have a look at the residuals. Okay, plot the residuals out for your models and study those. Okay, so if you do see some strange patterning within those values, then you know that a nonlinear model is more appropriate. You have several nonlinear models to choose from. You can go with what we call an exponential, which is here. You can go with a quadratic function, which is here. So a function with an x squared term in it. The highest degree or highest exponent being a 2. And then finally assess the appropriateness of the model. Check the context. Are you talking about population growth or decline? Are you looking at half-life? Are you looking at compound interest, radioactive decay? Like, what is the scenario? And in this case, it does not make sense for that function here to apply, okay? Because the time between 0 and 1, that population size would be bigger, when really it should not be getting smaller as time goes by, but should really be increasing. So there you have it. If you have any questions, please feel free to drop in and ask away.